Hi again, everybody, and welcome back, and welcome to the beginning of Chapter 11, our chapter on rotational dynamics and static equilibrium. Rotational dynamics is going to kind of be an extension of our last chapter on rotational kinematics. This is going to involve forces that are in play around rotating objects. Static equilibrium we spoke about in a previous chapter with regard to forces, but the static equilibrium, that is, a system being completely balance with regards to forces, is also going to be with regards to rotational systems. Okay, so equilibrium in rotational systems. All right, let's go ahead and get started. So our first idea in this chapter is that of torque. T-O-R-Q-U-E. Now, torque is indicated by a Greek letter tau. Some people say tau. I pronounce it tau, T-A-U. And it's this little, it looks like a pie sort of, but with only one leg and kind of a little loopy thing at the bottom. It's it looks mostly like a T, but it has a little curve at the bottom right there. What torque is you might say a force that is applied in a turning motion, or it's turning force. Your car, or maybe if you're a motorhead or something like that, you know all about torque. You know how much torque your car can put out. That is how much turning force or rotational force the car has at its wheels. And that is a product, we say it's a cross product of two values, right? The radius and the force that is actually applied. Now, both of these are vectors. Now, that radius obviously has that arrow over it, as does the force right there. And so if we multiply vectors together, we call it a cross product. Now, I'll talk a little bit later about what that actually means. But it means that if you, well, let me back up a second. If we take force equals mass times acceleration, okay? The force is a vector, the acceleration is a vector, mass is simply a scalar quantity, and so we're multiplying the mass and the acceleration. And so that means that the force is going to have to be in the same direction as the acceleration, as we spoke about, because the mass is simply just a multiplier right here. We have two vectors multiplied by each other, this radius and this force, both of which are vector quantities. The result is that this torque, tau, is it's going to be in a direction that is different, well, that may be different than either one of these two quantities, depending on how they're multiplied. Okay? So that's all I'll say about that for right now. But if you take the units for radius, that's distance, and force is, well, it's a force, I'm sorry, well, radius, distance being meters, force is newtons. We have the units for torque being Newton meters. Again, if you're a car person, you may measure torque in foot-pounds, all right? Or, well, I guess it should be pound-feet. Some people say foot-pounds, other people say pound-feet. Like I think my car that I just sold had like 400 pound-feet of torque. Very, very powerful car, all right? Well, pound is a force. Foot is distance. So same thing right here. But our units are going to be Newton meters. They're going to be the units for finding. They're going to be units for torque. Okay. So, like I said a minute ago, we're going to be talking a little bit more in detail about what a cross product means. And a cross product means if you have two vectors that are being multiplied by each other. It's not like the one is just a scalar, and you're multiplying the one vector, and it's being increased by a certain factor. No, the two vectors being multiplied together actually result in a completely new direction. And to kind of figure out what direction this is, we use what's called the right-hand rule. So if you take your index finger, all right, and you point it straight out, and then that's our first vector. All right, we call that, well, I'll do this in blue right here. Blue. Okay, so I'm going to underline our first vector in blue right here. That's our vector A, all right, straight out. And if the other vector that is being multiplied by it is at right angles to it, like our vector B right here, that would be your middle finger, all right, and that would be at right angles to your index finger. So if you make a right angle with those two fingers, your thumb just kind of has a tendency to stand straight up at a right angle to both of those right here. Right? So the right angle is that with respect to the B, and this with respect to the A right there. Sorry, I kind of buggered that up. But those are all at right angles to each other. You could sort of think of them as being x-axis, y-axis, and z-axis, or something like that. Well, the product of those vectors, A and B, is vector C. And we use what's called the right-hand rule to figure that out. So that tells us the direction of the cross product of those two. So let's do a little example right here. Okay? So you have an axis of rotation right here. Okay? And this distance out to the force, so here's a force, we'll call it mg, right, like a downward force. So say you've got a, I don't know, some sort of a hinge and a lever or a distance out, a radius out. In fact, let's just label that right now. Okay, that's our radius. And this force right here would be something that would have mass and being subjected to gravity. It's got weight, and so this object on the end of a rod that is on a hinge is going to kind of swing downwards, right? Well, what direction would the torque be applied in right here? Well, you have to use your fingers to do that. If this, let's see, this is our vector A. Okay, that'd be your index finger, all right? And this guy pointing downwards right here is vector B. So our radius times our force. Then if you're pointing this way with your index finger and pointing down with your middle finger on your right hand, remember it has to be your right hand, what direction does your thumb point in? All right, so you're pointing to the right with your index, you're pointing down with your middle finger. Your thumb is going to be pointing I can't write into. Sorry, in fact, I should write it a different color anyway, right? Because it's a different vector. Into the page. Or into the sheet or the screen. Right here, right? So the torque is kind of being applied. Let's see if I can draw like a little three-dimensional arrow. And like in that direction right there. That's really a bad three-dimensional arrow. But it's being applied into the page right there. Okay, so that would be the cross product of those two vectors, radius and force. Now, one thing you may notice right here is that the radius, which is going straight out, and the torque, the force, which is straight down, they're at right angles to each other. Okay? So let's pretend maybe this is, I don't know, a wrench or something like that. In fact, I think we'll look at a diagram in just a minute of a wrench. And so here's like a nut or a bolt that you're trying to turn. And so you're grabbing onto this lever right here, and you're applying a force downwards to try to turn it so that it will rotate the whole system, including the nut or bolt, around that axis of rotation right there. What you notice right here is that your force and your radius are at right angles to each other. But they may not always be at right angles to each other. So we need to account for that. So the total magnitude of the torque, tau, that we're going to be finding right here, is going to be vector 1 times cross product of times vector 2, or vector A, vector B, times the sine of the angle between them. Now I want to change this right here. Sine of angle between vectors right here. Let's change that theta. Not that theta is wrong, but remember in previous chapters, what did we use to symbolize the angle between two values? Well, we use a phi, right? Let's change that to phi and use that as our convention because we're used to that. All right. Typically, theta 10 in our course has been an angle simply based off of the horizontal. All right. Phi, I'll change this right here. That's going to be phi, and make this phi as well, and this phi right here as well. That's going to be our angle between the two vectors. All right. Now, if I back up just a second right here. All right, what's the angle between vector A and vector B? Well, it's 90 degrees, right? Okay, so the sine of 90 degrees is 1. Okay, so you're multiplying the full value of those vectors. vector A times vector B times 1. Okay, but it may not be completely 90 degrees. All right, if you are, let me back up again. If you're applying a force maybe, I don't know, in this direction right here, outwards, kind of with some component that is on the radial direction right here. See how this kind of has an X component to it as well as a Y component? First of all, you know probably from experience that isn't the most effective way to turn a wrench. But let's just say you would have an angle that is bigger than 90 degrees. Or it could be possibly smaller than 90 degrees, all right, from that first R vector right there. So this little guy or this big guy right here, bigger or smaller than 90, that's going to result in the cross product of your vectors being less than the product of their magnitudes. All right, so the sine of anything other than 90 is going to be less than 1, so you're going to be decreasing the total torque right here. So, in this case, if we have a force applied at a radius, then our definition of torque is going to be radius times the force sine of phi. That's really what this is saying right here. If vector A is radius and vector B is the force sine of phi, then that's going to be our definition for torque. All right, so let's take a look at a few quick diagrams right here. Like I mentioned before, here's our wrench that we're using to turn a screw or a bolt. And you know probably from experience that applying a force at right angles to that lever will give you the best, we call it leverage sometimes, right? Where's the best place to apply a force? Close to the screw or bolt or far from it? Well, far from it, right? Because it gives you the most mechanical advantage, the most leverage right there. What if you were to take your force and apply it? So you're trying to turn your screw or your bolt in, I don't know, the counterclockwise direction. What if you would apply a force out like this? What if that was your force right there? Well, you wouldn't get much turning done, right? Because only that component of it is really in the direction of the way you want to turn it. Much of the rest of this force, the other component, the complementary component of it, is really directed in an angle that is not in the direction of rotation right there. Or similar to if you're going around a revolving door, okay? These two folks right here have different amounts of leverage, but they're both applying torque. This girl is applying a small force at a greater radius. This guy right here is applying a large force at a small radius. And they're both applying the same, well, we can assume they're applying the same amount of torque. If they're going to apply the same amount of torque, he has to apply a greater force at a smaller radius. She has to apply a lesser force at a greater radius. But you'll notice that they are both at right angles to each other. That's a right angle, and that's a right angle right there. If this girl were to apply a force in that direction, or this guy were to apply a force towards the middle right there, they wouldn't get much turning done because that force is at anything other than a 90-degree angle from the radius, all right? So ideally, when we want things to turn or to apply torque to them, we want the force to be at a right angle to the radius that around the axis of rotation, all right? Which brings us to the idea of what we call the moment arm, okay? The moment arm. Now, last chapter, we talked about the moment of inertia, and that refers to how mass is distributed around an object that is rotating. The moment arm is, and this just might be a more convenient way to do what we just kind of talked about, is to think of the radius as being the radius perpendicular to the force. All right, or you might say it's the component of the radius that is perpendicular to the force right there. So instead of taking torque, here's what we had before. Torque equals radius, my vector arrows there, times force sine of phi. Here we're taking the sine of, this should be phi right here, and we're applying it to the radius. All right. What that tells us is that gives us sort of a hypothetical radius at which the applied force would be at right angles to it. And I'll show you that in just a second. Well, actually, I'll just sketch it right now, and then I'll show you probably a little more detailed diagram in a second. So here's our circle, very poorly drawn circle. And so here is our radius. Come on now, there we go. There's our radius right there. And let's say we apply a force outwards like that, okay? They're clearly not at 90 degrees to each other, right? But if we create a component of the radius that would be at 90 degrees to the force, so if the force were kind of extended back here a little bit, this right here would be what we call the perpendicular radius, or what we call the moment arm. So applying this force kind of at an angle that is off of 90 degrees from the radius would just be like saying, all right, well, we're going to apply the full force at a lesser radius that makes that a 90-degree angle between the two vectors right there. We call this the moment arm, or you could call it the perpendicular radius. That's literally what that sign convention means right there. But R perpendicular means the moment arm. So this is basically what I just drew right here. Wow, I didn't even really think of that. But here's our radius. Here's our force at some off 90-degree angle from the radius, okay? So if we were to take this angle between them, so this is our force, this is our radius, so this right here would be our angle phi. In order to get the moment arm, R perpendicular, really, we would take that R and multiply it by the sine of that angle right there. Okay, so instead of modifying the force, we're simply modifying the hypothetical radius around which that force is applied. Okay, well, I think that's going to be good for this section right here. I'm already coming up on 18 minutes, so I'm going to wrap it up here. But that is our introduction to this chapter on rotational dynamics and static equilibrium. So if you have any questions about this, please make sure you come see me. But in the meantime, thanks for following along. I'll see you on the next one.